Hello, everybody. Happy Fossil Friday, and welcome back to another episode of Fossil Friday Chats, hosted by the Western Science Center and the Raymond M. Alf Museum of Paleontology. I'm Brittany from WSC, and with me, as always, is my co-host, Gabriel
What's up,
Santos.
paleo nerds?
And today we are joined by Jordan Claytor. How are you doing, Jordan?
Good. How are y'all?
Pretty good.
Doing well, just sitting here with jealousy over your I know you don't particularly like it, but your fine weather in Washington State. We're in a drought here in California. We don't know what water is.
Isn't the whole West Coast on a drought though?
That's true.
I mean, not
Seattle
really.
anymore.
Oh no, you're not in a drought anymore. Okay.
Oh, good
We're
for
officially
you.
out of our drought.
Yay. We
Oh
love a sustainable ecosystem.
man, I miss Seattle. Anyway, before I get into that,
Anyway, so we are very excited to have Jordan here today, especially considering that Gabe and I are both mammal paleontologists. And so we're incredibly interested in the topic that will be presented by Jordan today. If you're not familiar with Jordan's work, Jordan is a fifth-year graduate student in Dr. Greg Wilson Mantilla's lab at the University of Washington. His research focuses on the ecology of mammals, yay, following the Cretaceous Paleocene mass extinction, specifically changes in diet and body size. Outside of research, Jordan is passionate about making paleontology a more diverse and welcoming field for minority students. So, yeah, we're super excited to finally have Jordan on the program today.
Excited to be here.
Yeah. And as always, everyone, if you have questions for Jordan after the presentation, go ahead and drop them in the chat. As always, we will have a Q&A session afterwards so that you can ask your questions and get some answers. So whenever you're ready, go ahead and take it away.
Cool. Okay, well, cool. All right, well, thank you once again for having me. Really looking forward to this. Yeah, so title to my talk is To Hell and Back, Mammal Time. A little bit of a pun there, because, yeah, you'll see. But I just wanted to first start with a land acknowledgement. All the fossils that will be shown in the presentation were collected on the traditional territories of the Fort Belknap, Assiniboine, Gros Ventre tribes, and the Fort Peck, Assiniboine, and Sioux tribes. So just to start with a little background about myself. Growing up, I have always been obsessed with the natural world. Anywhere from paleontology to like weather phenomenons to, as you can see here, catching any small animal that couldn't run away from me fast enough. And my parents really nurtured this love for the natural world and would bring me to the Smithsonian Natural History Museum basically every summer. Growing up in Maryland, it was a quick kind of train ride down, and they would just kind of let me nerd out in the Paleo Hall and the Mammal Hall and just kind of take everything in. And that kind of obsession continued as I grew up. And I got the opportunity to volunteer at the DC Zoo's invertebrate exhibit. And I worked there for about 3.5 years. And that kind of solidified in my mind that I wanted to go to undergrad and get a degree in biology. I just really didn't know what in biology I kind of wanted to focus in. But in 2013, I went down to North Carolina and started undergrad at Elon University, and then essentially spent the next 4 years trapped in this building, our science center. But it was probably some of the best 4 years of my life. I got some really great opportunities to participate in research related to kind of dolphins and birds and reptiles, but nothing really stuck. And it wasn't until I actually got the opportunity to go back to the Smithsonian and do an internship there that I really found my passion and kind of future career in paleontology. So while I was there, I got to work for 10 weeks with Dr. Matthew Carano on a project with some Judith River microvertebrates. And that kind of solidified in my mind that paleontology was kind of the discipline for me. And in 2017, I joined the Wilson Mantilla lab here at the University of Washington, Seattle, and have been working and kind of studying as a paleontologist ever since. So, if you know anything about the Wilson Mantilla lab, you know that the majority of our fieldwork happens in the Hell Creek region of northeastern Montana. And so if we look at this map in the upper left-hand corner, Hell Creek region essentially is the area that surrounds this town of Jordan, Montana. And present day, the Hell Creek is kind of the quintessential uh, image of the Badlands of the western interior of North America. So it's super arid and dry. The summers are incredibly hot, and the winters are really brutal and cold. But 66 million years ago, the Hell Creek region looked very different. So it would have looked something like we see in some of the Gulf Coast states, where it's kind of this swampy, humid, wet environment with all these large rivers and channels running through. And the reason for that was during the Cretaceous, the North America was bisected by this large inland seaway called the Western Interior Seaway. And the Hell Creek region was kind of right up on the margin of the seaway. And it's most famous for its incredibly diverse dinosaur fauna. So if you look here, we have everything from really large theropods to small theropods to animals like Triceratops, really large hadrosaurs. But the two that most people know from the Hell Creek region are Tyrannosaurus rex and Triceratops. And T-Rex was actually first identified in the Hell Creek region. And because of these kind of large dinosaurs and stuff, they kind of overshadow the other animals that are present in the Hell Creek region. But the ones I'm most interested in are the little tiny mammals that lived alongside the dinosaurs and then lived after the dinosaurs went extinct. So if we kind of just look at Mesozoic mammals generally, the mammals that lived alongside the dinosaurs, they kind of have this reputation of being these small, unspecialized animals that were just trying to eke out a living while the dinosaurs were kind of dominating the landscape. However, in the last decade or two, we found a lot of discoveries that show that Mesozoic mammals were actually pretty diverse and doing a lot of things ecologically that we don't really give them credit for. So this is a specimen here, and it's been interpreted to have a flap of skin that connects its arm to its leg. And because of that, some researchers believe it's evidence of gliding in Mesozoic mammals, similar to what we have in present-day mammals like the sugar glider. This one here in the middle, on its tail, it kind of has a morphology similar to what we see in some semi-aquatic mammals. And because of that, some researchers believe this is one of the first kind of semi-aquatic mammal species. And then this one here is really cool. When the fossil was found, they actually found evidence of another animal in its gut cavity. And they were able to identify those bones, and it was actually a juvenile dinosaur. And so this was evidence that mammals were actually preying upon dinosaurs during the Mesozoic. And so they were actually really diverse and doing a lot of cool things. And so in the Hell Creek region, we actually had three kind of major groups of mammals during the Cretaceous. And the first were our multituberculates. So multituberculates are often kind of dubbed the rats of the Mesozoic. They're super abundant, super diverse, and were everywhere. Multituberculates are actually the longest lived group of mammal, and they only went extinct as in the Eocene around 45 million years ago. And they're known for these really weird teeth. So on the left, the top two are the lower fourth premolar of these animals, so the lower premolar, and it formed this big blade. And they could use that to kind of slice their food open. And then below that is an image of their upper first molar. And these molars have these rows of cusps in them, and that's how they get their name, multituberculates. Our next major group are our Metatherians. So Metatherians are just a larger group that includes our marsupials. So marsupials are alive today, primarily in the southern hemisphere, and examples include kangaroos, Tasmanian devils, and there's one marsupial that's actually alive in North America today, the Virginia possum. However, during the Cretaceous, their relatives, the Metatherians, were super abundant and diverse in North America. And then our last major group are Eutherian mammals. And so Eutherians are the larger group that include our placental mammals. And placental mammals make up over 90% of the mammal species that are alive today. And they have the widest kind of diversity of ecologies. So Placental mammals include everything from bats to whales, to humans, to elephants. But during the Cretaceous, they kind of fit the stereotype of Mesozoic mammals of just being small insectivores, not really that specialized. And I just want to highlight in particular one of the mammals that we find in the Hell Creek region during the Cretaceous. This is an animal called Didelphodon. Didelphodon is a Metatherian, so part of that group related to our modern marsupials. And Didelphodon is notable because it has these really large bulbous premolars and molars. And because of that, it's been interpreted as a carnivore, potentially preying upon small dinosaurs. But those kind of large premolars and molars also give the indication that it may have been feeding on hard objects. And so Didelphodon may have been kind of a hard object specialist, either eating dinosaur eggs or potentially even shellfish, which I think is really cool. But all that came to an end at the Cretaceous Paleogene mass extinction event. So this mass extinction event led to the demise of all of our non-avian dinosaurs, so all the dinosaurs except for birds, along with our large marine reptiles like mosasaurs, pliosaurs, and our pterosaurs. It also led to the extinction of about 75% of the mammal species that were alive in the Hell Creek region. And this extinction kind of has two main causal mechanisms. The first being this kind of volcanic eruptions in India that were causing these wild climate swings towards the end of the Cretaceous. And then the final nail in the coffin was the asteroid impact in the Yucatan Peninsula. After a mass extinction event, we have what is called biotic recovery. And this is where my research really fits in. So I'm really interested in how mammals were able to recover from this mass extinction event and eventually diversify and take over the planet. And when we look at biotic recovery, we often look at it with kind of two metrics. So species richness, which is just like the number of species that we find in site, and then evenness, how evenly are these species distributed? Do we find 80% of one species and then all the other species only make up 20% of the assemblage, or is it spread a little bit more evenly amongst all of our species? And there's kind of four main categories, or four main stages of biotic recovery. First, we have our extinction event. Then we have what we call the disaster interval. And so each of these little mice here represents a different species, or each different color mouse represents a different species. During the disaster interval, we tend to have a low number of species. So in this case, we only have 3. And it tends to be that one of those or a couple of those species make up most of the assemblage. And so in this case, our kind of black mouse here is making up the majority of the individuals that we're finding in our kind of example disaster ecosystem. When we move on to recovery, what tends to happen is that you see more species start to appear, either by kind of diversifying in the area or moving from other areas into this area. And we start to see that our species are distributed a little bit more evenly. So here in our recovery, we see we now have the addition of the purple species, and our black species is not nearly as abundant as it once was. And then kind of our last thing is called our recovered interval, and that's when we start to see the same amount of species as we had before the extinction event, and evenness values that look like what it did before the extinction event. And so now we've added this kind of bright blue and dark green mouse species, and none of them are truly dominating over the other in terms of abundance. The Hell Creek region is a great place to study this because it actually captures the entire transition from the age of dinosaurs into the age of mammals. And so what we have is kind of the last 2 million years of the Cretaceous, the first million years of the Paleogene, and in the rocks we can actually see the boundary, and it's kind of in this dark layer of kind of coal that cuts across the landscape. Speaking of these coal layers, after the mass extinction event, we have numerous coal layers. And so if you look in the middle here, you'll see there's all these black lines, and they're labeled going from U down to Z. And these coals actually can be dated. And because of that, we can get really fine scale resolution insights into what mammals were doing after the dinosaurs went extinct. Two of them are really important to me. The first being this coal here, which has been dated to about 28,000 years after the mass extinction event. And this one here, which has been dated to about 80,000 years after the mass extinction event. And I'm really interested in what mammals were doing an interval in between. Are we still kind of in this disaster phase? Are they starting to recover? What are they doing, essentially? And so I've been looking at this interval, looking at 3 different localities. So our first one here is called Herpejunk. So where that white star is where the actual locality is and where we collect the fossils. And then black arrow is pointing out there's a dark band in the rocks there, slightly tilted. That's actually one of the coal layers I was just talking about. And that's the one that designates 80,000 years after our mass extinction. This one is my second locality called Morales 1. So it's a photo of myself and then 2 other researchers. On the left, Tom Tobin, and on the right, Luke Weaver. And then my last locality, Carey Paget 6, with 2 of former lab volunteers. And so we use Carey Paget 6 as kind of an example. How do we even collect these mammal fossils? Obviously, the mammals at this time were a lot smaller than the dinosaurs, and so the way we collect dinosaurs won't work with collecting these mammals. And so we kind of have to use a different set of methods. And so what we do is first find our locality. A lot of these localities were identified back in the 70s and 80s, and so we are able to use kind of field notes and GPS coordinates to find them year after year. And then we start a process called surface collection. And so we get down on our hands and knees or down on our bellies, and we kind of crawl in a straight line towards the locality, and we're trying to pick up anything that could potentially be a fossil. And we're doing this because every year the fossils get eroded out from the locality, spill out on the surface, and we want to make sure we're collecting all the fossils we can, and so we don't miss anything. And the easiest way to tell if it's a fossil or a rock is by seeing if it sticks to your tongue. Fossils will actually stick to your tongue, rocks will not. But once we finish surface collecting, we then look for what we call the productive horizon. So our lab manager, Logan, is using his hands here to bracket the productive horizon for Carey Paget 6. And this is essentially the layer of rocks that all the fossils are collected in and that are being eroded out of onto the surface. And so this is a layer of rocks we're really interested in collecting. And so what we do is isolate that layer and then bag it up in these large field sacks. So you can see in the photo here or in my background. And these can range anywhere from like 50 to 90 pounds. And we bring those back to our campsite. So every summer we camp along the Fort Peck Reservoir. And we use these big kind of wooden crates that are wood on all sides except the bottom where we have a really thin mesh, really fine mesh. And we leave it out in the water overnight. And what that does is essentially washes away any of the dirt and silt. And so what we're left with are any larger rock fragments and the fossils themselves. We take that, dry it out in the sun while we're out doing field work, and then bag it up. We bring that back to Seattle, and then we screen wash it again in a sink system that we have here in our lab. And what we're left with is what you're seeing here, kind of large rocks and any fossils that were in the productive horizon. So this just show, this is a couple of specimens of mammal teeth that we've gotten through this process of surface collection or what is called screen washing. And so on our left, we have our multituberculate teeth that I showed earlier. In the middle, we have our Metatherians or marsupial relatives, 2 upper molars of a species called Dilacodon. And then on the right are Eutherian or placental mammal relative. And if we just look across those 3 clades and in my 3 localities, you can see that multituberculates actually make up somewhere between 83 and 86% of the specimens that we find. Eutherians are in second place there with 11 to about 13%. And then our Metatherians are somewhere between 3 and 6%. And the really interesting thing is majority of the fossils we find that are multisporicoids are actually from the same genus. And it's a genus I've been showing throughout. It's called Mesogma. Mesogma by itself makes up close to 77 to 80% of the teeth that we find in these three localities. And so what this tells us is that these three localities are capturing this disaster interval after this extinction event. We don't have that many species, and if we look at evenness, it's being dominated by one genus in particular. However, even though our eutherians there kind of make up somewhere roughly from 10 to 15% of the assemblage, there are actually some really important eutherians that are popping up. So in particular, we have this group called the archaic ungulates. So on the left is an image of one called Tungulatum, on the right, one called Theoconodon. Both of these animals have been interpreted as kind of what we call immigrant taxa to this area. And so we have no record of them before the mass extinction event, and then they just kind of appear immediately afterwards. And so we kind of have this idea that they're moving in from a different area into the Hell Creek region. And these taxa are really important because they're showing that eutherians are diversifying more after the mass extinction than they did prior. They're moving into new dietary areas, and so these two have been interpreted as omnivores versus this kind of strict insectivores that we had before the mass extinction event. And these two have often been kind of talked about as being potential ancestors to a lot of the ungulate groups that we have around today. We also see the appearance of stem primates. And so within 100,000 years after the mass extinction event, this group of animals called the Plesiadapiforms pop up. And the first species, genus that we find is this genus that's shown here, Purgatorius. So this is a bunch of different molars and premolars from Purgatorius. But these animals are really important because they're actually, or potentially, sister group to all of the modern primates. And so for us to really understand primate evolution, this group is really crucial. And they seem to appear really quickly after this mass extinction event, and were potentially even present before the mass extinction event, but don't really start appearing in the fossil record till later on. And so kind of the next steps of this research is to untangle the difference between taxonomic and ecological recovery. So generally, when we talk about recovery, like I mentioned, we talk about it in terms of species richness and evenness, which are both kind of taxonomic metrics. But we can also look at it ecologically and try to see how mammals were diversifying through their diets or through their body sizes or locomotor modes. And we can also see if that diversification is happening at the same rate or at the same time that species are diversifying, or if it's slightly offset, like has been seen in some other biotic recoveries after other mass extinction events. So if we go back to the Hell Creek region, you can see that this is kind of the best place to study this really pivotal moment in mammal evolution. It's also one of the best places to find a lot of really large charismatic dinosaur fossils. But the Hell Creek is also a really great classroom environment, and our lab tries to take full advantage of that through a program called the Dig Field School. And so this is a kind of collaboration between our lab and the Burke Museum here in Seattle, and it's a professional development program where we take K through 12 educators, bring them out to the field, and they get hands-on exposure to scientific research. So they're actually working with us to collect data, and they're learning about paleontology in a really cool experience. And they get to bring all of these experiences and knowledge back to their classrooms and share it with their students. And so every summer, we bring out a group of 25 to about 35 teachers. They camp with us out by the lake, and they get to participate in a lot of these efforts. This was a photo I showed earlier of surface collection, and these are some of the dig teachers from our last year in 2021 doing surface collection at a locality. And just here's some of the fossils that they found through this process. And after they've collected everything, they get to work on identifying what these fossils are using some keys that we've put together. And this part's really important because after the dig program, the teachers go back to their schools. They're able to request a bag of sediment from the Hell Creek that we ship to their classroom, and then their students get to sort through it, find the fossils, and identify them themselves. And so here the teachers are getting firsthand experience doing that and kind of picking up any tricks or tips that they can share with their students to identify the fossils that they find. And while they're out there, we're kind of doing a mix of hands-on activities and these lectures on site at a lot of our different localities. Along with collecting the really small things, they also get a chance to work on some of our macro or large-scale collecting efforts. So here's a group from 2019 after they put a plaster coat on a theropod hip bone. And here's our group of teachers at a rock formation where you can actually see the boundary. And so there's kind of this black bar that goes across behind teachers that is host to our actual Cretaceous Paleogene boundary line. And so here they're getting a lecture from my advisor, Wilson Mantilla, and Tom Tobin on the history of discovering that boundary line and how that kind of changed the way we viewed this mass extinction. And at the end of this program, the teachers get a chance to present what they've learned to their peers and to us. And they also get a chance to chat with one another and talk about how they're going to incorporate all of this information they've learned and the curriculums we've provided to them into their classrooms. And we also have former teachers, the teachers who've done the program in the past, come back every summer and share their stories about how they were able to use this program in their classrooms. And so it's a really valuable experience for the teachers, but also for us instructors. It's just a really great time. We get to share all of our knowledge with teachers and really make some really nice and meaningful connections. Yeah, so that's the end of my talk. I just want to do a quick thank yous to my lab and the University of Washington Paleopod, the UCMPs and UW field crews who help collect a lot of these specimens, Burke Museum, collection staff, and some of my funding sources.
Awesome.
Yeah, thank you so much, Jordan. That was great.
I have to say, I really love the name Purgatorius. It's like, it's so metal, I guess.
It's evocative.
Like, especially because it's an early primate, right? That's just such a cool name for one of our early ancestors or relatives. It's just Purgatorius. I love that so much.
Yeah, it gets its name. There's a locality out there called Purgatory Hill, and that's where they found the first few specimens. And that hill is hell to get up onto, so its name is very fitting.
I was gonna ask if they named it that for a reason. Love the presentation. One of the questions that I had while watching it is, you talk about all of these different mammals that you're finding in the Hell Creek. I think there's a common conception that, after the Cretaceous extinction, mammals kind of took the opportunity. There's like this opportunity to really diversify and become more successful. Is that accurate? Is that kind of what you're seeing in the fossil record, that mammals are kind of proliferating in the specific absence of dinosaurs?
Yeah, so I think that was kind of our viewpoint for a while, but we're kind of seeing more recently that mammals are actually diversifying prior to this mass extinction event. And it may have been in tandem with angiosperms, so flowering plants. They first kind of appear at the end of Jurassic and then really start diversifying in the Cretaceous. And it seems like mammals were kind of diversifying in tandem with them, especially towards the end of the Cretaceous. So two of the groups, the multituberculates and Mesotherians, are actually diversifying really, really quickly and doing a lot of cool things with their ecology leading up to the boundary. And then the boundary kind of, puts an end to the Mesotherian diversity in North America. But then the multituberculates and Eutherians then kind of have that burst of diversification then afterwards. In the fossil record, the first 80,000 years is not really much much evidence of that. But as we start moving closer to 100 to 300,000 years, you start to see mammals really starting to diversify and move into a bunch of different now open areas.
I really love, because like, growing up for myself, the idea that mammals during the age of the dinosaurs were all kind of the same. They're either like kind of rat-like or squirrel-like, rodent-like, whatever. But like, yeah, they're all tiny. But like in the last, I don't know, decade or so, like the amount of discoveries we've had on the diversity of mammals just really, really is cool. And I love how you said that, it's suggested that they co-evolved or adapted with, flowering plants. As a plant person now myself, I love that mammals were already like back in the day already like, oh, cool plants. Let's go follow that.
We love these.
Do you think like in the before the extinction, or like before the extinction event with like a lot of the earlier mammals, if it were not for that evolution of like angiosperms or the flowering plants, do you think it could have gone in a very, very different way, just being very speculative?
I think so. I think angiosperms provided mammals two kind of really big things. A new food source in terms of plant, well, fruit and stuff, but then also insects were diversifying as well. We have the appearance of pollinators that kind of work in tandem with the angiosperms in their flowers. And so that's another food source for the mammals. But then also flowering plants provide like habitat in a way that's different than what we see in gymnosperms, so kind of pine trees and stuff, where they're creating multi-layered ecosystems. And so you can have animals that now are kind of specialized, live at the very top of the trees, or ones that live kind of in the middle and stuff. And by breaking up the habitat there, you kind of allow mammals to diversify even more. And so if you didn't have these plants, I don't think mammals would have nearly the amount of opportunities to diversify, and they may have kind of stayed smaller and not had this kind of ability to start moving into like plant-based diets and whatnot.
Cool.
I think the iDig program is really cool, bringing educators out into the field. Like, what are some of the like results that have come from that? Like, is that like, what have educators told you? Like, has that been really good for their classrooms? Are they really able to bring, paleontology directly to their students? What are some of the results of that program that you've seen?
Yeah, first thing we hear is that all their students think they're like the coolest person ever because they got which is really cool. But then the students get really excited themselves when they realize like, oh, now I can touch a dinosaur. There's a piece of a dinosaur in this bag of dirt. So I think the students like get this new connection to like paleontology. I think as a discipline, it's kind of like one you don't meet very many paleontologists. You don't really have that many experiences to like see paleontology. And so I think that has given a lot of students a chance to be like, oh wow, like this is an actual thing. It's not just like the crazy dinosaurs you see on TV. Like people are actually studying this. And I think it's been a really great way for a lot of teachers to maybe like shake up their curriculums or like adapt new kind of teaching standards. So like one of the big things with the DIG is that we are trying to like keep our curriculums up to date with kind of the next gen standards for education. And so by doing this, it's a way for teachers to kind of incorporate these new teaching ideas and styles into their classes in kind of a way that's maybe a little bit less scary of having to start from like ground zero. They're able to like have a program that's already kind of built around it and be like, use this lesson plan, we provided for you.
I love that so much. I mean, we were talking about before we went on air, but like the DIG program is so cool because like there's a perception of what paleontology is based off of movies. That's no one's fault. That's just how they kind of experience paleontology, right? Like not everyone, but a lot of folks may just think it's like people walking around. We find fossil just laid out beautifully on the ground and like we can brush it, or we're always finding these beautiful skeletons, but that is so not true. And I think it's really cool to give folks this experience and change their perceptions of like the science of paleontology, the techniques in paleontology, and really get people to understand the kinds of work that go into these amazing discoveries, like our early mammal ancestors, but it took, I'm going to assume, Jordan, it took many months to screen wash and sort those fossils, having done it myself.
Yeah, I think in my first summer I collected close 400 to 600 pounds of sediment from about 6 different localities. So at that point, I had more that was going to include. 3 of them just never produced any mammals whatsoever, and then the other 3 did. But I think majority of that is still like unwashed and unsorted, just kind of sitting in our collection spaces.
Oh man, I love screen washing. Don't get me wrong.
It's fun.
It's fun. It is, and you get
It's
messy and like you can do things.
Yeah.
But I'm also jealous that you can just submerge your stuff in like a lake overnight and just let it wash out. Like that is
much less labor intensive.
It is, and I'm very jealous. Like, I mean, when I was doing my master's thesis, like we had like an automatic like shaker that we could put it in like a little tub so that it can like do the shaking for us at least. But I had to change the water out like every hour because it got so muddy and clay that it wasn't moving. So I saw that photo and like, our cameras are off what you were doing, but I was like up on the screen like, oh my God, that is so cool.
It's really great until it's like 6 a.m. in the morning and you have to go out in the water and bring them back in. It's like
okay.
But yeah, it makes it a lot easier. We're able to break down a lot of those bags and make it a lot easier to bring back to Seattle. And so there have been years where like we had to bring a U-Haul truck to like bring all the bags of dirt that we collected back to Seattle. But we try to break it down as much as possible. And then once it's back here, we have an army of undergrads who do most of the screen washing for us.
Nice. It's experience, right?
Research experience, yeah.
Exactly. All right. Well, we have a question from Fossil Friday Chats alum and new paleontology curator at the Alf Museum, Dr. Belisi, who says, "Hi, Jordan. I enjoyed your talk. Thank you so much. How are you thinking about tracking the ecological diversification in addition to the taxonomic diversification post-extinction?"
So with the mammal fossils that we have, we're kind of limited on what we can look at with their ecology, just because we primarily find their teeth. I don't know if I said that during the presentation, but I'd say like 99% of the fossils that we find in these mammals are their teeth. All of the smaller kind of postcranial stuff breaks and falls apart, or if it's not associated, we can't really tell them apart. But with the teeth, we can get kind of 2 really big metrics. We can look at body size, just based on some kind of measurements of the teeth compared to modern mammals. And then we can also look at their diet. And so what we're planning on doing is creating these eco spaces where we have diet on one axis and body size on the other, and looking how mammals fill that kind of eco space prior to the mass extinction event, and then looking at a sequence of kind of localities after the mass extinction and seeing how they change their kind of distribution. And what we're seeing so far is that for the mass extinction event, you have majority of the mammals kind of in this a little bit smaller body size categories, and they're either faunivores or animal dominated omnivores. And after the mass extinction event, you start to see them moving more towards the corner that's larger body sizes, a more herbivorous based diet. So we have some of them who are becoming strict herbivores, and a lot of them that are becoming more plant dominated omnivores. And so that's how we're planning on tracking kind of the changes in ecology. And all these sites, we kind of already have these taxonomic metrics on, so we can compare the rate of kind of species change, increase through time to kind of how they're changing and occupying different niches of ecospace through time. Hopefully that makes sense.
No, yeah.
No.
It's just, you just brought me back to my master's thesis for a little bit. That's why I was just like,
he was like, oh man.
Oh geez.
Right back to grad school.
Well, because like you were saying, and I was thinking about a question that I had. I was studying Eocene, so it's much later than your stuff, but I was still just like, just brought me back for a question that I have to go maybe look into again, because I haven't done that. I haven't published my master's thesis at all. So anyway, that's not enough about me. There's a question in the chat from Tara Neal, who's asking, where is Hell Creek? For folks who may not know what that site is.
So it's this area in northeastern Montana and North Dakota. And so the Hell Creek is its rock formation that essentially captures the last 2 million years of the Cretaceous. And the area where the rock formation is kind of exposed in, we just refer to as the Hell Creek region of northeastern Montana. And so it's around kind of centered. Most of the researchers come into this town of Jordan, Montana, and then spread out from there.
Cool. Like when you went out, like what was like, because for paleontology folks, the Hell Creek is kind of like a big deal. It's like a cool place
Mhm.
to go. What was it like when you saw like kind of like that boundary for the first time, like in person?
It was, for lack of a better word, like just kind of crazy because after like my first year of grad school, we talked about this boundary, talked about all these coals and stuff, kind of learning the area. It was really different when you're finally out there and like looking at the rock formation and be like, oh, those are the coals you were talking about. And like, I think it finally put everything together in my mind. The boundary line in particular was really cool because it was just like this moment in history that changed the entire course of the planet. Um, and it's just preserved so nicely in this like nice little line of the rocks, and it just looks so harmless. But you know, there's just so much horror that went along with creating that.
I love because like, for a lot of folks they think paleontology is just the bones, right? But geology is so important. It's like it's the basis of most of paleontology, and folks don't realize is that we can literally see time when we look at like cross sections and like outcrops of geology, and like you said, it seems harmless. It's literally just a line in the rocks, but that is that is one of the worst days on the planet Earth, right? It's one of
Mhm.
the five worst days on the planet Earth, and it's just so cool. It's right there, and you can literally see that change in time and read. How do we like? We read the chapters of time through rocks, and so
Yeah,
I love geology so much, and I really
Mhm.
wish we could get more folks to realize like how awesome geology is when it comes to paleo.
Right, and then, like, it's necessary in that you can't tell a lot about many fossils without their geological context, which is why it's like when paleontologists go out the field, we take a ton of notes. Because if you don't have that context, you're missing a lot of the story of that bone. A bone by itself oftentimes, isn't gonna tell you the full tale.
yeah, definitely. And where we do field work too, having that understanding of the geology, in particular those coals, has been so valuable for
Mhm.
us. Having this really like fine scale. I mean, in the fossil record, we talk about things on like the order of millions of years a lot of the times, but to be able to get to like 28,000 years, the fossil record is just crazy.
That is so cool how you can like find that really beautiful specific piece of time like right there. It's like for a lot of like you were saying, Britt, like people can just go find fossils and like kind of get a basic understanding of something, but without that, what's the word? Provenance, right? Yeah, provenance
Mhm.
of where it came from. That's where so much of the data is, and so
Mhm.
if you're an avocational or amateur paleontologist out there and you're going like learn to read those rocks if you can, and take if you're not experienced in it, like there's classes or there's the dig field school
Mhm.
where you can learn kind of stuff like that. So it's just so fun.
All right. We have another question. This one is from Carl. Do many or any of the pre extinction event mammal species carry over the boundary line?
Yeah, so we do have a couple species that are survivors. So that one that's super abundant after the mass extinction, genus Mesodma, they were around prior to the mass extinction event as well. Um, and then what's it called? We have a couple that weren't present before the mass extinction event, but we think they're just descendants of animals. Um, so we have a couple with one Megatherian. Megatherians get hit really hard at the boundary. They were probably just as diverse as the multituberculates prior to, and they get reduced down to one species after the mass extinction event. And then our Eutherians, there's one or two that were ancestors were present pre-mass extinction, and then their descendant was present after the mass extinction event. But a good number of the species that we find afterwards just kind of appear out of nowhere after the mass extinction event. We're not really sure where they came from, but they're here now.
Surprise, we lived. Do you have a hypothesis, Jordan, as to why like some of these mammals were able to survive that mass extinction event?
They've kind of been, the ones that survive are small, so they're definitely on the smaller end of the scale of any of the Mesozoic mammals that we had. They're also pretty much all generalists, so they were able to eat probably a range of diets from whatever plant material was left over to insects, and were probably pretty good at scavenging anything that was on the landscape. Yeah, and there may be something to do with multi-tuberculates and their kind of reproductive strategy. One of my old lab mates, who's now a postdoc at Michigan, Luke Weaver, has kind of looked into this somewhat. But that may be kind of an area to look into and figure out. Might explain why multi-tuberculates in particular were able to survive and proliferate so much after this mass extinction event.
Cool.
Here's another good question. This one is from Daniel. When did the first true mammals appear in the fossil record?
Oh, that's a debate.
It reads like such a simple question, but not truly.
Yeah, I guess it kind of goes back to whether we count as a mammal. If you're counting stem mammals, you could say the end of the Triassic. If you're counting kind of true, what we call crown group mammals, so the last common ancestor between placental mammals, marsupials, and the only group, or third group of mammals that are alive today, the monotremes, probably back somewhere in Jurassic. But yeah, mammals have been around essentially the same amount of time as the dinosaurs. But what's it called? In various forms. Walking on eggshells with that question.
Really, I was about to admire the way you distilled that debate into that answer. You're like very deft.
Well, I think that's important to know, right? Like it's paleontology. We're piecing the past, the story of the past, on like tiny bits of evidence, like considerably of like how much life has existed and how long life has existed, and we only get these tiny fragments of evidence of life, and so we're trying to piece it together. So the more evidence we find, the more the story will change and the more clear it'll become. So I think it's totally fine that we don't know, like we're debating, and I think that's part of it, and it's fun. Well, it's mostly fun depending on who you're talking to.
Well, it goes back to what Jordan was saying earlier about how the way that we thought about mammal diversification has changed. Paleontology is not a static science. This is something, we haven't discovered everything. And so that's why we need future paleontologists to be able to continue this work, because we're always finding out something new, and what we understand about the ancient world is changing all the time.
Yeah, definitely. And I think, what's it called? Mammal research, especially in the Mesozoic, is kind of in this like renaissance where we're finding all these really cool discoveries, and it's really changing the way that we kind of interpret the fossil record. And I'm sure in about 10 years, the answer to when mammals appeared and what counts as a mammal, all that kind of stuff will completely change from what we kind of understand it now.
Do you think, like in the past, like during the early time of paleontology and the dinomania, do you think there were like mammal fossils that people just like didn't even like think about and just tossed away? Like it's kind of like, it's like hard to think about, but there probably was, right? Like
oh yeah. I mean, early fieldwork in the Hell Creek Formation or the Hell Creek region, before people realized like we have the boundary and there's going to be a whole area where there's no mammal fossils, people would kind of walk around that area, just kind of discount it because you're not finding dinosaurs. And it's like, yeah, but the mammals are doing cool things.
Again, we are very, very pro mammal on Fossil Friday Chats.
Well, here's the question that we ask every speaker who comes on Fossil Friday Chats. What advice would you give for people who are interested in becoming paleontologists themselves or getting more interested in paleontology? What would you say to someone who's interested in this field?
I would say don't be afraid to reach out to paleontologists that you see online. I think there's kind of this scientists I think aren't always portrayed as like the good guys in a lot of pop culture stuff, and so I think people maybe see us as a little bit unapproachable, but we're all really nice, I promise. So if you see a paleontologist like in a YouTube video or online somewhere, just like email them and like ask them your questions and stuff. They're more than likely going to respond and help you kind of figure out what the field is. I was really lucky growing up to have the Smithsonian kind of within a 30-minute car ride, and so that was really pivotal in me kind of getting exposed to even paleontology, like being a field. And so I think if you have access to like natural history museums and stuff, they're a really great resource, and they have a lot of programs, especially nowadays, like online too, to really learn more about paleontology and stuff if you can't get to like the physical building itself.
Oh yeah.
Also, the internet's become a really great tool. A lot of paleontologists are taking to Twitter and like TikTok and stuff to like share their kind of what's it called knowledge and passion with the world.
Most of us are big nerds, present company included.
Who are you calling a nerd? God. Okay, fine.
So to say.
I mean, it's literally on my shirt, so.
I
know. Well, thank you so much for the advice, Jordan. Thank you so much for this really, really cool presentation. I mean, like just seeing again, like all the cool mammals that existed, and hopefully some people had not even heard about before, which is so fun. And again, Purgatorius, top tier name in my opinion now. If folks want to get in touch with you, where's the best place for them to find you online and things like that?
I am on Twitter at the Oxyprimus. What's it called? Oxyprimus is another one of the species that we find, and that's actually my favorite name of an animal out in the Hill Creek. So, yeah, on Twitter, or just email me. It's called just jclaytor at uw.edu, and I'm happy to chat.
Cool, yeah. We'll make sure we put those in the description below. Also, I love how so many paleontologists like social media name is like kind of their favorite taxa. So like I'm Paleoparadox, Paleoparadoxia. Brittany, you should change yours to some horse theme.
I know. Now I'm gonna have to choose between all my horsey children.
Or you could be the prehistoric horse girl.
Just oh my gosh, I do have I that's actually pretty good.
I just put it online, so you better hurry before someone takes it. Anyway, thank you so much, Jordan. Thank you so much to everybody at home for tuning into Fossil Friday Chats. If you like this program and want to support programs like it at both the Alf Museum and the Western Science Center, you can find links on how to do that in the description below. And as always, make sure you like and subscribe for more stories from the world of paleontology. Thank you all so much, and we'll see you in 2 weeks. Bye, everybody.
See ya. Thanks for coming.